All right, so we are looking at day 3 today. This is our cardiorespiratory system, which is obviously a big part of very relevant to talking about like fitness assessments, right? We are going to assess someone's cardiorespiratory capabilities and, how well their cardiovascular system is functioning. So if we're looking at this, we're going to understand like the cardiorespiratory system in a nutshell. After this presentation is over, we'll be able to kind of describe the parts of our cardiorespiratory system, which is going to be made up of primarily your cardiovascular and respiratory systems, respectively. So we'll be able to kind of describe the structure and functions of those, how they relate to like human movement. Obviously, we wouldn't be able to move if we weren't able to like produce our own energy. But at the same time, like how we move also affects how well we can bring in oxygen. Like if you have elevated shoulders and a forward head posture, that poor posture can limit how much oxygen you can drive into your lungs. That's going to be a big part of what we talk about today. We'll talk a little bit about like oxygen testing and things like that. And then we'll talk about like how all of that relates to like us producing energy for movement. So if we look at our cardiorespiratory system, it is going to be comprised of the cardiovascular and the respiratory systems. So, we use the term cardiorespiratory. This is a mistake, by the way. I just want to address this right now and get it out of the way for any of my new students who haven't fallen into this trap yet, because I think almost any anatomy student falls into this trap at least once. You're going through your test and you're reading really fast and you're trying to get the questions done. Do not fall for the cardiorespiratory and cardiovascular systems being somewhat similar. People will get like halfway through the word and then they'll skip to the next one, and they'll put the wrong definition down and stuff. So remember, your cardiovascular system is your heart, blood, and blood vessels. It's in charge of like generating pressure, delivering nutrients around. Your respiratory system is in charge of extracting oxygen from the environment. And your cardiorespiratory system is the cardiovascular plus respiratory systems. And that is responsible for extracting oxygen and delivering that oxygen. So gathering and delivering oxygen throughout the body. So, it's kind of a classic. I've definitely seen students in the past, be like, which of the following systems is responsible for gathering and delivering oxygen? And, your cardiovascular system cannot gather oxygen. It can just deliver it. And so they'll put like cardiovascular system because they'll kind of see it in, brain fart or move too fast. So warning now, don't do that. They work together in order to provide your entire body with a means to extract nutrients, deliver those nutrients, remove waste products from the body. And, your blood has like protective, like that's where your immune system or a large part of your immune system is. So there's that as well. So the cardiovascular system is your heart, your blood, and all of your blood vessels, right? So you've got the pump sending stuff around, the means to, like what is getting sent around, that's your blood, right? And then blood vessels, which allow your body to have like a place to travel. So when we look at like the pump, right? If we look at the heart first here, it's a muscular pump that must rhythmically contract in order to drive blood throughout the body. So when we say that it's a muscular pump, your heart has its very own like special type of muscle. It's made up of special muscle fibers that we refer to as cardiac muscle. So cardiac muscle and skeletal muscle are pretty similar, but there are a few key differences, right? You've got 3 types of muscle in your body. Like your organs are also like muscular, right? We don't really think of it like, I'm not doing like bicep curls with my small intestine or anything. But like your digestive system is squeezing to move food throughout your body, right? It's making these small little contractions, right? So your organs that make up your digestive system are made up of what we call smooth muscle. And we call it smooth because it doesn't have very many striations in it, because it doesn't have as many of those contractile proteins that we normally see in like a normal muscle, right? Like a muscle is made up of like muscle fibers, which make up fascicles, which make up the overall belly of the muscle, that isn't going to be quite as present in smooth muscle. So it's not going to have as strong of contractions. Well, your heart is kind of like in between those two, right? Like it's not going to create as strong of a contraction as like skeletal muscle will, like my heart can't squat 200 pounds, but my glutes and quads can, but your heart does need to be able to contract for a really long time. So it does have a lot of mitochondria. It does have a lot of like blood vessels covering the whole thing. It is very good at producing enzymes to produce aerobic metabolism. Heart muscle is termed cardiac muscle, and its characteristics are somewhat similar to skeletal muscle, right? All the muscles throughout our body, but a little bit different, right? Cardiac muscle is going to have actually, it's going to have less nuclei. It's going to have less nucleuses running throughout the heart cells, which is kind of surprising because you're like, oh, that's kind of weird. Like nuclei kind of helps you produce energy, like on the, or tells you to keep producing energy on the go. Why is there less nuclei in cardiac muscle? Well, remember, like your heart's main job is to generate pressure, right? Like it needs to be able to generate maximal pressure, which means that all of the fibers that make up your cardiac muscle need to be able to fire simultaneously. They need to be able to like what we don't want to have happen is like some of the fibers in the heart squeeze at one time and then other fibers in the heart squeeze at another time. If that happens, your heart starts to get out of rhythm and you aren't generating maximal pressure. This is actually, we have a term for this that we call fibrillation. And it's when your heart is basically quivering. And it's because like the fibers in the heart are not able to fire simultaneously. Instead, they're kind of firing randomly at all, like, different times. There's too many cooks in the kitchen. It's Gordon Ramsay's worst nightmare. So that's actually why you see like in movies and stuff, they do the paddles, they'll go clear, and they like zap somebody, or, this is part of the reasons why we need to know how to use an automated external defibrillator. If a client starts experiencing like a heart attack, like fibrillation, we need to be able to like hit them with a burst of electricity. And that now understanding like why that works actually is a part of understanding like how our heart works. So your heart works just like any of the other parts of your nervous system. It works through a series of like electric signals, right? Like in skeletal muscle, your nervous system creates an action potential, which triggers an action potential in your muscle, which triggers a muscular contraction, right? That's also going to happen in your heart. Electricity is going to run in. But what's interesting about your heart is your heart actually has, and I won't go too far into the chemistry lesson side of this, but like, remember, the way we generate electricity is by pumping sodium and potassium ions in different levels, and that creates charge, right? It's kind of like taking batteries and flipping them, right? Like that's generating electric charge. We're using sodium and potassium to do that, right? So your heart actually has these channels as well. It has like sodium and potassium channels in order to be able to like generate electricity, but it has leaky channels. It's actually like when sodium gets pushed in one direction, it naturally wants to rush back in the other direction, and it can because those channels actually leak, and they leak on purpose. So what's interesting about your heart, because it's something that we want to continuously pump for our whole lives, is that your heart is able to generate its own electricity, which causes it to pump, and that pumping causes it to change shape, which pushes sodium and potassium in another direction, which creates electricity, which creates the next pump. Right? It's a big circle, right? Like pumping allows your heart to pump, and it can't pump without the pumping. It's a paradox. It's a big circle, right? It generates its own electricity, and that electricity stimulates itself. So that's what's kind of cool about your heart's rhythm. And we obviously have seen that heart rhythm get messed up, like that's oftentimes like what a heart attack is. If somebody's fibrillating, right, their heart is not squeezing effectively, and all the fibers are basically quivering at different times. So we have a special thing in the heart here, right? We have this specialized little node. Actually, good Lord. Oh, I'm 3 slides away. What do you? Man, today is a weird day. I got sick. My mouse is acting up. If we're looking at the rhythm here, we'll use the space bar. Your heart fibers, they are more tightly connected, right? Because they need to be able to like contract together all at the same time. We want to have simultaneous contractions because simultaneous contractions result in stronger contractions, right? They're able to generate more pressure. And so it needs to be in sync with each other. So your cardiac muscles have a built-in rhythm. That built-in rhythm is going to be about 70 to 80 beats per minute. So the typical heart rate of adults is about 70 to 80 beats per minute, okay? So you're gonna typically go about 70 to 80 beats per minute. But obviously when you start doing exercise, what's happening is like you are increasing the acidity throughout your body, right? You're generating lactic acid by doing a bunch of like movements. That lactic acid is then gonna run by your heart actually, and your heart's gonna go, oh man, that's some acidic blood. So what it'll do is it'll go, we need more oxygen to be able to process all that lactic acid. And so then you'll start breathing a little bit harder, and then your heart will start pumping a little bit faster. And that faster pumping is now going to, now that you're breathing harder and more oxygen's coming in, that elevated heart rate is now pumping more blood throughout the body to process all that lactic acid from all that work. And that way you can keep doing work, right? Look at that. What? What is going on? Am I just not allowed to be on this slide? Is it because I changed the transition? I cannot believe, like, I don't need technical difficulties on the day that I like nearly threw up. Nope, stop it. Right? There, nope, there. Oh, I went, okay. Slide 8. All right. So, I don't know what I did wrong. I would have time to fix it, but if we're in the middle of this call. All right, so your typical beat is gonna be about 70 to 80 beats per minute, right? That is gonna be controlled by your heart's rhythm. Now, what actually controls your heart's rhythm is going to be this specialized little structure called your sinoatrial node. So if you look at your sinoatrial node, it is going to be located in your right atrium. So if you look at your heart here, that's not one I like. There it is. There we go. So here's your heart, right? This is your right atrium right up here. You've got your right ventricle, then you get your left atrium and your left ventricle, right? And then that's going to pump blood all the way throughout the body. We'll talk about those chambers here in just a second. So if you look at your sinoatrial node, this guy right here is responsible for starting that electric signal. You see all these yellow, they almost look like wires, right? These little wires running throughout your heart. Those are all of what we call your internodal pathways, right? So basically that is where all of the electricity is able to generate throughout the heart. So when your sinoatrial node starts the electric signal that triggers your heart's contraction, it will then move along the rest of the heart. And you'll notice there's a little AV node over here. That's your atrioventricular node. And this actually delays your signal for a second. And that's what allows you to contract the upper parts of your heart and relax the lower parts. Then the lower parts of your heart are able to contract, right? And that drives everything in. So basically your heart's able to go bump, bump, right? It has this little bit of like timing to it. And that timing is really important because that's, again, generating areas of high pressure and areas of low pressure. And now blood is naturally going to want to flow from an area of high pressure to an area of low pressure, right? So looking at that here, typical heart rate is about 78, 80 beats per minute. The heart rate is controlled by the sinoatrial node. So the sinoatrial or SA node is responsible for controlling the heart's rhythm, right? So your sinoatrial node is triggering when your heart is going to actually contract. And this is located in the right atrium. We typically refer to this as the pacemaker of the heart. Right, so this is the pacemaker of the heart because it is responsible for setting the pace of your heart, right? When your heart needs to increase, your SA node is what activates that, right? Now, there are some other ones here as well. There's internodal pathways, your atrioventricular or AV node, and then there's also like the bundle of His, which is the coolest name ever. But basically, those are all of your internodal pathways that allow like your whole heart to get like all the signals it needs, you know? Similar to a motor unit, right? We know that one neuron controls multiple muscle fibers. So you need multiple neurons to control multiple muscle fibers. You have multiple like internodal pathways here. But the SA node is going to be sort of the most important that we talk about. Oh my God. So then we look at our heart chambers, right? So looking at your heart chambers, what? No. Yeah, let's go to here actually. So chambers of the heart. Now, this is the stuff that sometimes gets a little bit confusing just because it's a lot of labeling. So for all my new folks, we got to get like our categories down first, then we'll break down like the specific versions afterwards. So your chambers of your heart that you have got atria or atriums, right? Which are going to be chambers that gather blood. That's what like an atrium does. Now, there are going to be two of them. You have got your right atrium, which is responsible for gathering blood that is returning to the heart from the body. Okay, so your right atrium gathers blood as it returns back from the body, right? Then you've got your left atrium. So if this gathered blood coming back from the body, which means like if it came back from the body, that means that it's all deoxygenated, right? Like all of the oxygen that was in that blood has now been used up. And so now that blood needs to get over to the lungs where it can pick up some more oxygen. Once it picks up that oxygen, now it's going to get back out to the body, right? So it's going to travel back to the heart, and the heart is going to gather it first in the left atrium. So your left atrium is responsible for gathering blood that is returning to the heart from the lungs, right? So now we're getting our blood back from the lungs so that it can get out to the body, right? And then it's going to come back and drop back into that right atrium and complete the circuit. So those are what your atria are. They are gathering sites for your blood. And you can think of that, right? When you think of like the word atrium, right? If you picture like, anybody ever watched the Beverly Hillbillies at Nick at Night? I used to watch that with my parents all the time. You know, they had like a big mansion. You see it like a lot of mansions, you walk in and there's that big spiral staircase. You're in an atrium. You're in this like gathering site where you can, you know, be escorted by the butler to wherever it is you're going. I don't really know anything about actual mansions. But like that is what an atrium is. It's a gathering site, right? So atriums, the top two, they're going to gather blood as it's returning back to the heart. And that blood's either coming from the body or coming from the lungs. Then you've got your ventricles, right? These are chambers that pump blood out of the heart. So this is the real muscular part, right? See this like really muscular section down here? Those are your ventricles, right? And you can see there's a whole bunch of tissue. That's all the cardiac muscle. Now you'll notice that like this left ventricle right here, which I know is on the right side of your screen, by the way, Remember, this is from the anatomic position, so it's the left side space. It's facing away from you. So that always gets a little confusing. But this is your left ventricle right here. And this, you'll notice there's a little more tissue, right? Look at how muscular this side of the heart is. You know how we place our hands over the left side of our heart when we're doing the Pledge of Allegiance or national anthem or whatever, right? The reason we do that is because like we think that the heart is located on the left. That is not true, by the way. Your heart is located pretty much dead center, but it does point slightly to the left, which you can see here. And that's because the left side of the heart's a little bit heavier, so it kind of tilts in that direction. So that is the much more muscular part of your heart. So your left ventricle needs to be more muscular because your right ventricle is going to pump blood to the lungs. Your left ventricle is going to pump blood all the way down to your right pinky toe, which is a far ways away from your heart. Your lungs are right here. Doesn't really need to pump all that hard to get blood a couple inches, but getting blood to travel many feet or to travel up to your brain against gravity, you know, that is going to require a much more muscular part of our heart. So when we look at this, right, we've got our right ventricle, which is going to receive blood from the right atrium and will pump blood out to the heart, right? So blood has returned from the body to the right atrium. Now it will drop into the right ventricle where it will then get pumped to the lungs, right? Then that blood's going to come back from the lungs, gather in the left atrium, drop into the left ventricle, and get pumped to the body. So your left ventricle is going to receive blood from the left atrium and will pump blood out to the body. So here's my advice to you guys. Memorize what the chambers are, right? Ventricles pump blood away, atriums pump blood or gather blood that has returned, right? Memorize that. And then pay attention to just one ventricle that you get into your brain and memorized really well. Like if you just remember the left ventricle pumps blood out to the body, well, then logically, if you've got a right, left ventricle and a right ventricle, if the left ventricle is pumping it to the body, we know that you'll remember that the right ventricle will pump it to the lungs, right? Because it's going to do the opposite. And if you remember that like a ventricle pumps blood, an atrium will gather it, and left is going to be attached to left, and right will be attached to right. So you can literally, if you do forget these definitions, as long as you have one of them memorized, you will be able to sort of like a puzzle figure out the rest, right? Any questions on those chambers so far? Any questions at all?
No, sir.
All right, I will do, one thing I will do, let's look at we'll do a blood cycle here. We'll do blood flow cycle. So we'll go let's start with right atrium. So right atrium, it will then travel to the left atria, good Lord. Right atrium will go to right ventricle, which will then travel to the lungs. Then it will travel to left atrium, to left ventricle, to body, back to right atrium. Okay, so there's our kind of cycle. I wish I had that. Normally I do this in a circle. Normally I do this like in like a big circle on the whiteboard. But basically it's like from heart to lungs to heart to body to heart to lungs to heart to body. It's kind of a figure eight more than it is like a circle, right? So that's kind of the overall cycle. It'll start in your right atrium, it'll drop into the right ventricle, it'll get to the lungs, it'll come back to the left atrium, left ventricle, body, and then it'll return. Of course, I forgot that was happening. Chapel or Valentine's heart. Yeah, yeah, that's true. I cannot draw. Susan's calling me out because she knows better. I cannot draw an actual heart to save my life because I am horrible at drawing things. But I can draw Valentine's Day hearts and then put chambers in them, and it works. You know. Let's see. Let's look at this. I'm sure somebody else has done this. Valentine's heart with chambers. It's somewhat close. Nobody's done it. That's, oh, wait, kind of. Oh, is your heart broken? Oh, that's kind of sad. All right, let's look at that. All right, maybe I'm the only one. But I mean, you can fit like, you know, chambers inside like the flares of a Valentine's Day heart. See, kind of. All right, moving on. We get it. I'm bad at drawing. So each contraction will sort of pump that out. Now, talking about what that contraction is, we got to talk about like what our heart's rhythm is, right? So we've talked a little bit about like the chambers. We've talked about like the blood flow cycle here. Within that chambers. Now let's go ahead and look at the heart when it's actually functioning, right? So function of the heart, okay? So your heart does have like two main components in terms of how it functions, right? Like when we think of like measuring the functionality of the heart, and this, by the way, is like really what's relevant to this course, right? When we think of like how our heart's actually functioning, we're going to measure it in two ways. We are going to look at how often it beats and how much blood it pumps per beat, right? Those two things determine how functional our heart is, right? Like if our heart can't pump very much blood per beat, then it has to inefficiently pump more often in order to get the job done, right? So each contraction is going to push blood to the body. The amount of that blood that's going to be pumped is going to be is your cardiac output, right? That's the overall volume of blood that is being pumped per minute, right? And so that's going to be made up of heart rate and stroke volume. Volume of blood, number of beats per minute equals cardiac output. So function of the heart, right? We're going to refer to this as cardiac output. This is the overall function of the heart. It is comprised of heart rate and stroke volume, right? It is the volume of blood ejected by the heart per minute. So there's a couple different ways to actually, rather than saying overall function, we're going to say overall performance because that's what they say in your textbook. It's how your heart's actually performing, right? So there's a couple different definitions here that you will be likely asked on your NASM. You'll get one or more of these, right? It'll say like blank is the overall performance of the heart, right? That's cardiac output. Or they'll say the volume of blood ejected from the heart per minute, right? That's cardiac output. Or blank is comprised of stroke volume times heart rate. That's cardiac output. So there's a couple different ways they like to ask questions on this one. So let's go ahead and define each of those separately, right? Heart rate is going to be the number of beats in 60 seconds, right? So if your heart rate is, that's how often your heart is beating, right? That's your actual rhythm. And then you've got stroke volume, which is the volume of blood ejected by the heart per beat, okay? So heart rate, number of times it's beating in 1 minute's time. Stroke volume, how much blood is being pumped per beat. Now, we can't really measure stroke volume, right? Like, at least not very practically in a gym setting. We can't measure how much blood is being ejected by the heart. But we can measure your heart rate. And because we know that it's an equation, right? Like the performance of your heart, the function of your heart is made up of stroke volume and heart rate multiplied together, right? Actually, I should put that formula down here. Yeah, let's put that formula real quick and then I'll finish what I was talking about. So cardiac output, which we label as Q, by the way. The formula is going to be Q equals heart rate, or HR, times stroke volume, or SV, right? So that looks HR, or Q equals HR times SV. You will sometimes see this equation here, right? Cardiac output. It's labeled as Q, by the way, which I always thought doesn't make any sense. But the reason for that is because it's the quotient of blood being pumped. Oh, we lost somebody. Oh, where the heck is everybody? So that's going to be your cardiac output formula. You want to know the formula just in order to be able to spot it. You don't need to be able to actually like do the formula or anything. You're not going to have to do any math on your NASM test, but you need to be able to like spot that formula because they might ask you it. And the reason we need to know it is because like I can't measure somebody's stroke volume, right? Like I can't measure how many milliliters of blood are being pumped out of your heart every time your heart beats. But what I can measure is your heart rate. Like I can take your heart rate. And if somebody's heart rate's really high, well, then I know that their stroke volume is really low, right? And this is why resting heart rate, like somebody's resting heart rate, the lower your resting heart rate is, the more fit that we consider that individual. It's one of our measures of fitness, right? Somebody who has a low resting heart rate. The lower your resting heart rate, that means that your body can deliver blood really effectively because it can squeeze and pump a large volume of blood very easily versus a heart that's like squeezing really weak and not pumping as much blood out of the heart. Does that make sense to everybody?
Yeah.
Does that track?
Yeah.
Cool.
Yeah.
All right. So that is your overall function of the heart. Yeah. When you're monitoring your heart rate, by the way, there's two ways to do this. You can place your index and middle finger around the inside of your neck. That's how you do your measure your carotid pulse. However, NASM doesn't really recommend that because it's really invasive. You're like, you know, giving somebody, pressing your hands on their neck. Also, if they are exercising, you know, their heart rate's elevated, they're breathing really hard, you can close off their windpipe by pressing too hard, and then all of a sudden they can get woozy and pass out. So generally, we aren't going to use the carotid pulse. Instead, we're going to use the radial pulse. So the way that you measure that is by using your index and middle finger in line with your thumb and index finger on your left hand, okay? So that is the typical way that we measure. And then if you're getting somebody's resting heart rate, like if they're at rest and they're just kind of chilling, not really working all that hard, the easiest way to do it is to simply like measure it for about 6 seconds and then add a 0 on the end because you're trying to get the number of beats in 60 seconds. So if you do it by 6 and just multiply by 10, boom. So you measure their heart, it pumps 17 times. That means that their pulse rate is about 170, right? Which means this person's exercising pretty hard. That's a convenient way to like generally monitor pulse like mid-workout, right? Like if you're mid-workout, like let's say your client's on a treadmill and you're teaching them how to like measure their heart rate and stuff, you know, if they're running, you know, they're working really hard and they present you their left wrist, there's an awkward motion while you're still trying to run, right? And you're going to measure it. You don't really want to do it for the full 60 seconds. You kind of just want to get their heart rate really quickly and then move on. So that's how you're going to do that. You're going to do 6 seconds multiplied by 10. Now, we are going to, when we get to assessments, talk about variations of that. For instance, the 3-minute step test, I want to know what your heart rate is after it has recovered for 60 seconds. So, you know, that's a recovery pulse. That's very different than what we're talking about here. All right, so next one we're going to talk about blood. So looking at the heart here. Anybody remember that video? The kid was super cute. All right, so blood is another part of your cardiovascular system, and it is going to act as a medium to deliver and collect essential products to and from the body's tissues. Okay, so blood is how, this is obviously your heart's pumping blood around, but blood is going to, have these specialized materials in it that allow your body to gather and deliver nutrients and oxygen, right? You get roughly about 5 liters of blood in your body, which is about 1.5 gallons at any time. You can donate about 1 liter of that and still be okay. If you ever go to donate blood. But obviously what happens if you lose like a lot of blood, your body's gonna have to take time to produce more, which is why if you ever donate blood, you don't wanna exercise later that day because you're not gonna have very much blood to deliver very much oxygen, which means you're gonna probably pass out. So it's really good at transporting oxygen, it's transporting hormones, glucose, all kinds of nutrients throughout the body. It's also going to help you regulate your pH levels, right? By like transporting water wherever it needs to go. That way we don't get too acidic or too base throughout the body. It's going to protect you from injury, like if you cut yourself and blood's going to start leaking out, and it has this really cool ability to coagulate and turn into like a scab basically. That keeps all the blood plugged inside of your body. It's like it's like plugging a hole in a rowboat. I live in a cartoon. Those are all my examples. And then it's going to have all kinds of like specialized immune cells as well that allow your body to kind of fight off foreign invaders. So blood's really cool. It's got a lot of really big functions here. Big things we need to talk about that are relevant to us. You are going to see things like hemoglobin, right? Which is a protein present in blood that binds to oxygen in order to allow for blood cells to carry that oxygen to the body's tissues. So hemoglobin is really cool. Hemoglobin is this protein. It contains molecules of iron, in order to bind to oxygen. I trapped myself in a corner with that sentence. So hemoglobin contains these molecules of iron, right? Iron is why actually your red blood cells are red. When oxygen and iron bind together, that turns bright red. And that's why, pans rust and things like that, is because they've got some iron in them, and that's what allows them to rust. And so like, when you have like lots of oxygen in a blood cell, it's going to be bright, bright, bright red. This is why if you ever cut yourself, it looks super bright red. But if you look at like the veins in your arms, you'll notice that they kind of look a bluish color. Your blood is never, ever blue blood, by the way. Like, let's just go ahead and dispel that myth really quickly. You do not ever have blue blood. We draw it as blue because that represents, really, 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 really dark red blood, meaning that there's not very much oxygen left in your blood. So the reason it's so dark is because there's no oxygen activating those iron molecules. And then when you mix like dark red blood with like the pigment of your skin, we get kind of a bluish color. And that's why we think that our blood vessels like look blue. Again, though, you do not ever have blood that is blue. If you did, you would be a starfish. Blue blood, it's going to be pull up that TV show, found in starfish. Check this out. This is kind of cool. I don't really want to see a picture of a starfish bleeding. But take my word for it. Yeah, I don't want to see somebody like cut a starfish. But starfish actually don't use iron to bind their oxygen molecules. Instead, they actually use copper. which is why their blood actually is going to be a bluish color. Because when copper binds to oxygen, it turns a kind of bluish green, which is also why the Statue of Liberty is greenish. Fun little weird facts found throughout weird bodies. So, all right, so we've covered the heart, right? We've covered blood. Now let's go ahead and take a look at blood vessels, right? This is the last part of our cardiovascular system. So blood vessels are a closed circuit of hollow tubes that allow blood to be transported to and from the heart. So we have like what is called a closed vascular system, right? We have a closed series of tubes that are responsible for allowing blood to actually travel, right? So those tubes, they're all interconnected, right? We don't want to like break any of those tubes, because what that does is that decreases pressure, right? When you break a tube, now everything can leak out of there, and that creates like this area of low pressure, because there's all this space for like blood to flow, compared to when it's in your tubes where there's like very limited space. We want that limited space because that's what forces blood to travel in whatever direction we want it to travel in. So we do not like it when you break a blood vessel, right? That's why, you know, it's not deadly, but it's also not good for you when you experience like a bruise, you know? Bruising is basically where you broke a whole bunch of capillaries, those capillaries started leaking, and now you're seeing like a pooling of blood. That blood's not really gathering any oxygen, and that's why it's like that dark bluish color. Again, kind of coming back to the blue blood myth. So we have two primary types of blood vessels here. You're going to have arteries and veins. So this is very similar to the heart. So we've got arteries, which are going to carry blood vessels that carry blood away from the heart, okay? So an artery will always, always, always carry blood away from the heart. Now, the most common arteries that we tend to think of are, you know, like the arteries that are carrying blood right out of the heart, delivering oxygen throughout the body. So a lot of times people will assume that all arteries are oxygenated blood, right? And you can see here, like, look at traveling out of the heart. That's a whole bunch of oxygenated blood, right? Traveling out of the heart, that's a whole bunch of oxygenated blood. But remember, you are also pumping blood to your lungs because it doesn't have any oxygen. So you do have what are called pulmonary arteries, and that is pumping deoxygenated blood away from the heart. So don't pay attention to whether it's oxygenated or deoxygenated. That's a really common kind of rookie mistake that people make when they first start studying the cardiovascular system. Pay attention to what direction it's traveling. If it's away from the heart, it's an artery. If it's towards the heart, it's a vein. Now, there is like a small meeting place in between these two. Like there's kind of a small branch of arteries that we're going to call arterioles, okay? Arterioles are smaller branches of arteries. I don't like how I wrote that. Branches off of arteries. Ugh, I don't know how I want to say this. Come on, brain, use some English. Arterioles are blood vessels carrying blood away from the heart that have branched off of arteries. There we go. That's a little bit better. So basically, these are just like arteries, except they're smaller, right? They're much smaller in size. They have much lower pressure, thinner walls. Now, eventually, your arterioles are going to branch off even smaller. They're going to get smaller and smaller and smaller. They're branching, you know, more and more and more. That's causing them to get like even tinier. Eventually, they will form what are called capillaries. So capillaries are microscopic blood vessels that have that form beds to cover body tissues in order to be the exchange site for oxygen and other nutrients. So basically, right, you've got arteries, right? Your arteries are really large, and then they'll break into two. Now they're a little smaller. They'll break into two. They're even smaller. They'll break and they'll break and they'll break and they'll break until they are really tiny, microscopic tiny. And then what will happen is once they're small enough, they'll kind of form this like spider web bedding covering your actual tissues. And that's actually where we are exchanging blood, right? Basically, those blood vessels are going to lay on top of your tissues, and they're going to be able to, like, you know, push some things like through into those tissues and then pull some things out from those tissues. Once it pulls that stuff out, right, that's pulling like waste products out like carbon dioxide. So say a capillary pushes some oxygen into a body's tissue. That tissue produces some ATP, has some waste products left over like carbon dioxide afterwards. And then that carbon dioxide will get picked up by that blood cell into the capillary bed. And then it will travel from the capillaries. It'll kind of work its way back from the really small tubes into larger and larger and larger branches, you know, where more and more and more blood is kind of coming together until eventually it gets back to the heart, right? You can kind of think of it as like driving, right? Like you start on a really big freeway, then maybe that branches off into a small highway until that branches off into like a small like street, right? And that's where you park your car, go to your store, get out, you know, and then drive back. You go from the street back onto a highway, back onto a freeway, right? So arteries are really, 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 really large. They are your largest, most muscular blood vessels. They branch into arterioles, then they branch even smaller into capillaries. And now when it's on its way back, you've got your veins, right? So veins are going to be blood vessels that carry blood toward the heart, okay? So arteries carry blood away, veins carry blood too. Again, rookie mistake that people sometimes think is they think veins are always deoxygenated. You've got pulmonary veins, right? Blood that is traveling back to the heart, but has a ton of oxygen because it just left the lungs. So don't fall into that trap. So you also have smaller versions of these, which are called venules. Venules are kind of like arterioles in the sense that they're a smaller branch, but arteries branch off into arterioles. Venules branch together to become veins, right? So it kind of goes in the reverse order. So these are blood vessels that carry blood toward the heart after that have branched together. Wait. Oh, from capillaries. Yeah. So your capillaries come together, they get a little bit larger, they come together, they get a little larger, they get a little bit, come together, and then eventually we don't call them a capillary anymore, we call them a venule. Then they come together, and eventually we don't call them a venule, we call them a vein. Okay? Does that make sense to everybody? Pretty good on all that? Cool. Let me look up a picture of all this, by the way. Yes. What's up?
Pulmonary.
What's that? Oh, did we just lose Jay mid-sentence? Jay got Thanos'd. Jay, come back. There he is. Hey, we lost you.
Yeah, crazy, man. This just cut me off.
We lost you mid-sentence. What's up, man? You had a question. Oh, buddy, your connection. I can't understand anything you're saying. Can you type it? Can you chat bubble it? Maybe text it. Sorry, I'm just, it's so broken up, I can't. You sound kind of like a robot. Well, the chuckle I heard fine.
Can you hear me now?
Oh, you know what? There you go. Yeah. What's up?
Okay, okay. Pulmonary arteries and pulmonary veins both are oxygenated. Is that correct?
No, 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 no. Pulmonary veins, right? Remember, veins are going away from the heart. So pulmonary veins are deoxygenated. They have no oxygen, so they got to get to the heart.
Right.
I'm sorry. Blah. Pulmonary arteries, right? That's blood. Remember, an artery always goes away from the heart. So arteries that are pulmonary are deoxygenated. They have no oxygen. They got to get to the heart. Veins, typically veins are deoxygenated, right? Like they're traveling from my wrist where it did some work, it has no oxygen anymore. It's got to get back to my heart. But a pulmonary vein is going back towards the heart, but it just picked up a whole bunch of oxygen.
Okay.
So pulmonary veins are very oxygenated.
Oh, okay.
Yeah.
So is that
It's the
what is
reverse.
that? So that's what provides oxygen to the heart.
Yeah. Well, it provides getting blood that is oxygenated back to the heart. You're like providing oxygen to the heart. You might be thinking of like your coronary arteries.
Right.
Coronary arteries are arteries. They are ejected from the heart, but they are on this super short loop that immediately just like loops back onto the heart itself. And that's how your heart tissue gets oxygen.
So that's the only artery that goes to the heart.
Yeah, your coronary arteries. Yeah, it's a series of small arteries that give the tissues of the heart blood. Because your heart's not extracting oxygen from inside the chambers. Like your heart's filled with blood, but it's not actually like those heart tissues are not like receiving oxygen from the chambers. They're receiving oxygen by the blood vessels, just like any other tissue. It's just like your coronary arteries are no different than any other arteries, right? They branch off and eventually they become, these smaller versions, and they form a bed covering your whole heart, and they deliver oxygen, just like any other tissue.
Kind of
It's
like
just
capillary.
they're just the most important because they're the thing keeping the pump alive.
Okay, perfect.
So here's a picture, by the way, for you guys to visualize, right? So let's say like oxygenated blood is leaving the heart because it's got to go get to your foot, right? So it's going to leave and then, travel down an artery, down your leg, down what's called your femoral artery. And then that will branch off into smaller blood vessels called arterioles. And then it will cover the tissues of your foot. It'll deliver a whole bunch of oxygen in these little tiny blood vessels. And then you see how they'll start to branch together. Like this branch meets that branch. They'll come together and form venules. And then those venules will all come together to form much larger blood vessels, which are your veins. And veins are a little special, by the way. Veins actually have these specialized, oh my God. These specialized little valves in them, which we don't see in other blood vessels. And it's because veins are much smaller than arteries. So the pressure is much lower. And a lot of times, like, your veins got to work against gravity to get all the way from your foot back to your heart. Do you think that your heart is sucking with enough, whenever it relaxes, you think there's enough pressure to suck blood all the way from your foot up to the heart? Probably not. So it has these special little valves inside of it that are kind of just like a flap that sits kind of passively like this. And then what happens is like when blood pumps, it sort of pushes that flap like that, and then it kind of rests back in this position here. And so then it like pushes and then closes down. And that way, like if blood gets pumped up above that valve and then kind of falls back, blood pools for a second, and then the next heartbeat happens, and that pushes it open again, and then it kind of closes down again. And that way, like blood can kind of, work its way up slowly, higher and higher and higher until it eventually gets back to your heart. So that's the cardiovascular system in a nutshell. Do you guys have any questions about that stuff? All right, let's do the lungs. Let's talk about breathing. All right. So finally back to the first line. All right, the respiratory system. So, how did I define this earlier? Oh, I just did okay. All right, so your respiratory system is going to be made up of two primary sections, right? So if your respiratory system is responsible, going all the way up here, for gathering oxygen, right? And providing, a super oxygen-rich environment for all of that blood that we mentioned in the last half of this lecture. It has to be able to like provide this big environment for all of that blood to pick up a whole bunch of oxygen molecules. So its primary role, and this always sounds like a little surprising here, but its primary role is to allow for proper cellular functioning. Like that definition makes a lot of sense once you hear why, but sometimes you're like, wait, what do you like? That seems a little weird. Like, isn't its primary function to deliver oxygen? Well, it's like, why do you think you need that oxygen, right? You need it in order to deliver oxygen to your cells. That's how our cells are able to breathe and live through a process that we call cellular respiration, right? We call it cellular respiration. We also call it normal respiration, right? Like you're breathing. It's the small being an example of the large. So, the primary role is to primary role is to ensures proper cellular function by providing a means to gather oxygen from the environment. Okay. And obviously it works very intimately with our cardiovascular system, right? I cannot remember. There it is. Okay, so so the two primary sections that you've got are going to be your respiratory pump and your respiratory passageways. Respiratory pump's pretty easy to understand. That's like your rib cage, right? Your diaphragm, the lung sacs themselves, right? Like all of the stuff that allows you to actually kind of pump things, right? And the respiratory passageways are like your trachea and all the branches here, right? That's a passageway for oxygen to be able to travel. And again, it kind of starts with like these really large branches. We call these your bronchi. And then those bronchi break into bronchioles, kind of similar to like arterioles, right? So smaller branches of bronchi become these little arterioles. And then those really small branches are covered in these little sacs right here that are called alveoli, right? So alveoli are these little popcorn-shaped sacs. And you'll notice, it's kind of hard to see here, but they're covered in capillaries. So if we look at alveoli here, you're gonna see there's these little popcorn shaped, that's a great picture. These little popcorn shaped sacs, and look at how many blood vessels, like see these little capillary beds, they're covering the whole thing. So that allows for the transport of oxygen. So here's the thing. Here's what's really cool about like our respiratory system. By having all these little tiny branches like this, like it branches out smaller and smaller and smaller and smaller and smaller, what that does is that increases surface area. And so what I want you guys to picture right now, in order to kind of understand what we mean when we talk about surface area, picture like a big blank empty room. And that big blank empty room, it's gonna take one bucket of paint to cover, right? You're gonna dip in there, it's gonna take one bucket of paint. I'm gonna paint all my walls here, right? I'm gonna paint my ceiling, I'm gonna paint my floor for the sake of painting the floor. So there it is, like I covered it, it took me about one bucket of paint. But what would happen if in this room that I've got here, I were to put like a little tiny wall, in between, like just like a flat, right? Like kind of a random flat wall here, right? Now, if I'm gonna paint all the surfaces, I gotta paint all the walls, and I gotta paint like this random, like, wall that's sitting right here. I gotta cover that in paint. I gotta get the back side of it. I gotta get the top, the sides there, right? Now it took me more paint, right? It had more surface area. If I had another wall in here, I'd have to paint that as well. So by having smaller and smaller and smaller branches, what that does is that increases the surface area. Now, there's not just one surface for oxygen to be able to for capillary beds to cover, for then oxygen to be able to move into the blood. Now there's millions, trillions of little branches that allow you to have increased surface area, right? So it's a branch, a branch, a branch, a branch, a branch. That allows for literally trillions of oxygen molecules to get inside the body, right? So we love that surface area. And this is another reason why we talk about like why smoking is so bad for us. What will often happen when you look at these little alveoli, right? They're these little like sacs that look like this, right? Those little popcorn shapes, they have like these little holes inside here. Now, if you were to, let's say like cough really hard or breathe really hard, and you actually broke the wall in between these two, you would have kind of this odd figure eight shape, right? Like let's say we just break this little branch right here. You know, there's still a tube here. Oxygen's still going to be able to travel in, like no doubt about it. But now that you connected these two, this little bit of increased surface area from here and here, right? You just lost 25% of that, right? So that's kind of what we're going to see here when we look at like lung disease, right? Lung disease is where the membranes between them have broken down. So now there is less surface area. Less surface area means less blood flow. Less capillaries covering it, which means less oxygen flow, right? You're going to be able to get less molecules of oxygen in. And that's why, you know, strengthening your heart and lungs is so important. You want to be able to, you know, extract plenty of oxygen from the environment and deliver plenty of oxygen from the environment. So that's what we're talking about. We're talking about respiratory passageways. That's this super high surface area, you know, situation. By the way, earlier we were talking about having like, you know, we have a closed vascular system. There are animals that don't have closed vascular systems. They don't rely on blood vessels, like spiders, for instance. That's kind of a weird one. And so spiders actually have an open vascular system. When their heart beats, it basically just splashes blood around their entire body. And that's like what delivers oxygen. This is why Spider-Man could never exist, by the way. If we were to swing at the speeds that like Spider-Man swings from building to building, all of our closed vascular system, we would pool blood in the back of our head and then like pass out. That's why people pass out when they're on like space shuttle. They do that thing on the space, like, you know, astronauts, they get on that chair that spins them around like crazy. That's what causes them to pass out, is all the blood is pooling. And so then their brain is like, I need blood over here. And so it causes them to pass out as sort of a protective mechanism. So luckily, we have a closed vascular system that makes us not spiders. Also, luckily, you know, we have lungs. A lot of insects don't have lungs. They actually diffuse oxygen straight up through their body. And like, this is a good thing. They are able to literally like just kind of diffuse oxygen. One of the reasons we don't have giant insects anymore is because there's a difference in our atmosphere. We have less oxygen present in our atmosphere. That's what keeps bugs from being able to grow the size of like a human being. We have these really large bodies, like we have really large mammals because of our, you know, because of our respiratory system being the way it is. Thank God. Otherwise we'd have, you know, like, you know, crickets running around the size of lobsters. So anyway, let's go ahead and look at the respiratory pump here. So your respiratory pump is going to be divided into two primary sections. Oops, hold on. Respiratory. Right. This is going to be located in the thoracic cavity. AKA rib cage. It is responsible for providing the framework and flexibility to allow for ventilation, right? Or breathing, right? Which is our big fancy word for saying breathing, right? So you've got this really cool like rib cage here that is able to kind of expand and open up and contract and relax down, right? You got two phases here. You have got inspiration, which is inhalation or the driving in of gas, right? And then you've got expiration, which is also known as exhalation, or the expelling of gas, right? So you're either bringing a whole bunch of gas in, or you are, pumping a bunch of gas out, right? So you've got some bones here. No. You've got things like your sternum, right? That breastbone. You've got your ribs, and you've got all of your vertebrae, which also like move around a little bit in relation to your breathing. You can just start to understand like why it's so important to understand this when we look at like poor posture, right? Looking at that respiratory pump, we have got those bones. You're also going to see certain muscles. Your diaphragm is the most important, right? That is this kind of dome-shaped muscle that actually, when it's resting, sits in a position kind of like a dome like this, and it sits underneath your lungs. Then when it contracts, it flattens down like this. It actually flattens itself down. By doing that, it draws your lungs open, right? It literally contracts down to create an area of low pressure. It's like opening up a sack and air rushing into it, right? That's what's happening in your lungs. So your diaphragm's a really big, important part of that. Now, your external intercostals, your intercostal muscles are actually these little muscles that sit between each of your ribs, providing stability for all of those bones. Your scalenes, which are these little neck muscles up here underneath your trapezius muscles, your sternocleidomastoid, and your pectoralis minor, right? Those are all muscles responsible for breathing in, but the intercostals, the scalenes, sternocleidomastoid, and pec minor, all of those are what we refer to as secondary respiratory muscles. They're there to help when you're breathing like this. Like they're there to assist and open all that stuff up, but they're not supposed to do like a lot of work. Just like your secondary respiratory muscles, like your internal intercostals and your abdominals, right? They're there to like contract and push air out of your lungs. They are secondary. They're not supposed to do most of this work. Your diaphragm should be doing 90% of your breathing. But we have a lot of clients who experience like shallow breathing patterns. When we get stressed, remember, stress is a fight or flight response, right? So let's say a mountain lion jumped through my window, right? I'm going to be in a very severely stressed situation. I mean, chances are I get kind of excited. I'd be like, oh, kitty. But that is not the right reaction to have, right? I'm probably going to get stressed out. My body's going to go, oh, danger, right? And so what it'll do is it will start immediately going into fight or flight mode. And fight or flight mode is like, all right, we need to bring in lots of oxygen. If we need to bring in lots of oxygen, let's start breathing really hard. Let's start using all of our respiratory muscles that we can. Right now we're bringing in a whole bunch of oxygen. Now I can do a whole bunch of like work, right? Now my muscles have enough oxygen to do massive amounts of work. That's really good. We're really glad that we have that. But the problem is the world that we live in, right, isn't really filled with mountain lions anymore. It's instead filled with taxes and bills and showing up to work on time. And so what'll often happen, or, getting that spreadsheet filled out in time for your 2 o'clock meeting. So it's filled with stuff like that, which causes us to kind of do those shallow breathing patterns that are not so great for us, right? Those shallow breathing patterns are, causing us to use our secondary respiratory muscles. Well, here's the thing. Your sternocleidomastoid is also responsible for craning your head forward. So when you do those shallow breathing patterns, you are shortening the muscles that give you poor posture. And the muscles that give you poor posture are also causing shallow breathing patterns. It's kind of a bad circle, right? It's a positive feedback loop of awfulness. So we want to avoid that as much as possible by using our diaphragm, which is why I want to encourage our clients to breathe into our stomach. Now, we have also got our respiratory passageways. And these are going to be, you know, the actual like section where oxygen is able to travel. So these are passageway ways that are able, that allow oxygen, well, we'll say gas, that allow gases to be able to travel into and out of the lungs. Okay, so when we're looking at that, you've got conduction passageways. That's going to be like your nose, your nasal cavity and your oral cavity, right? You can both breathe in through your nose and through your mouth. You've got your pharynx and larynx, right? Those are the sections traveling down your throat. Your trachea, which is that kind of cartilaginous tube. See that in movies? You need, you know, the emergency tracheotomy where somebody's like, "Give me a pen," and they puncture it. You know, that's your trachea. It's this kind of cartilage framework. And then you got the main sections here that are going to branch down. These are your bronchi, right? So your pulmonary bronchi. So if we look at that, not bronchitis, just bronchi. So if you look at your lungs here, there's your trachea. It branches into these two really big tubes here. And then those branch into smaller sections, and then those branch into smaller sections, and those branch into smaller sections until it gets microscopic. So I got to say it branches into smaller sections for the next hour or so. So that is your conducting passageways. And then you've got the actual respiratory passageways, which is your alveoli and your alveoli sacs, right? So your respiratory passageways are going to be your conduction conduction passageways, which are things like your trachea. I'm just gonna put the trachea and bronchi, which are those main tubes. And actually, we're going to put bronchioles there. I know it's a little bit off compared to the PowerPoint, but those are the main ones that are important to us, right? So trachea, bronchi, and bronchioles. Then you've got your respiratory passageways, which are going to be your alveoli and alveoli sacs, right? Actually, we can just put alveoli sacs. So the little sacs covered in blood vessels, right? So that is the anatomy of everything. We've kind of labeled everything out now. And that's really most of what they're going to ask you questions related to. They just want to know that you know these structures in these chapters. Later on, we'll get into the function, right? Like, we need to know about this because, you know, when we get into, like, let's say you're training somebody for the first time, right? You're doing your fitness assessment. And I asked you, I was like, "Susan, does your job cause you a lot of stress?" You might be like, "Why does that matter?" You know, like you're like, what does that have to do with like me moving and exercising? Like, you're supposed to tell me what stretches to do. Why would my stress level have anything to do with what stretches to do? Well, because of our understanding of anatomy and physiology, we know that when somebody is stressed, they breathe like this. Look at my neck, right? Like, look at my scalenes are all stretched out. That is not awesome, right? Like, that is not what we want to have. So we know that these are the type of stretches you need to do in order to get you back to feeling better, you know? So that is a big part of it. All right, now that we've kind of got the anatomy out of the way, let's finally dive into our second section of the day. Technically, like, we've all been under like really only one big section here. So looking at the cardiorespiratory function, right? Now that we know what everything is, let's talk about how it works, right? So your respiratory system is going to provide the means to gather oxygen from the environment, and your cardiovascular system is going to provide the means for transporting all of that oxygen. We already really put that up here. right? Cardiovascular system, actually responsible for gathering and delivery. Yeah, we put it up there. So let's go ahead and look at actual oxygen consumption here. So this is something that gets a little scary just because of how much like this is very numbery. So the average amount of oxygen consumption, right? The amount of oxygen that the body consumes is going to be 3.5 milliliters of oxygen per kilogram of body weight. So the more you weigh, the more cells you have. The more cells you have, the more oxygen you need. On average, the oxygen consumption for a human at rest is 3.5 milliliters per kilogram of body weight. Now that is at rest. So when you are working harder, you are going to be burning more energy. This is often referred to as what is called a MET, by the way. That's sometimes referred to as like a metabolic equivalent. So, right, MET. So METs are basically like when you are fully at rest, like let's say you're sleeping, you are burning like 1 MET at a time, right? But if we look at like exercise here, right? Volleyball, you're burning like, you're at like 3 METs, right? Playing volleyball really casually. Seriously, volleyball is lower than golf? Whoever made this chart has not played volleyball or golf. Both of those are, very different from each other. I'm going to go ahead and pick a different example. I did not like that at all. That made me uncomfortable with that person's sources. All right, here we go. Yeah, working at a computer is like 3 minutes. I was going to say, like, who's casually, like, that's like somebody laying down and be like, hit me with the ball. And then maybe they're raising their arm. So reading or like sleeping, for instance, that's about 1 MET. You're burning like 1 MET at a time, right? You're burning about 3.5 milliliters of oxygen per kilogram of body weight every minute. Now, when you're playing an instrument, that's about 2 METs, right? Sitting upright, working on the computer, maybe that's about 3 METs. If you're gardening, 4 METs, right? Running is like 8 to 10 METs. So when we think of that, right, like why is this relevant? Well, you think of it as like, I like to use it as a motivational tool. Like most of my clients don't really care about their METs. Your clients they're just not motivated by that kind of stuff. They're motivated by how many calories they burn, But obviously the more METs you are the more METs you're burning, the more oxygen you're consuming, which means the more calories you're burning. So what's kind of a fun thing about METs is, and you guys have seen this, by the way, if you ever get on the treadmill, it'll say, what speed you're going and then how many METs you're working at. What's kind of cool about that is like, if your client's jumping rope, you can tell them, it's like, hey, did you know right now you are burning 7 times the amount of energy that you would be if you were like sitting at home just watching TV right now? That's kind of cool. I like to use it as like a motivational factor. Now, it can also be really helpful to use in like long distance racing. If you're burning through METs too quickly, you're going to burn through your fuel source too quickly. So you want to slow your pace down a little bit. But I like to use it as like a motivational, like taking the stairs is burning 6 times as many calories as taking the elevator. That's pretty cool. I like to use that as kind of an example, or at least 3 times as many, because standing upright's a little bit harder. So we do want you to know this. I've had students come back and tell me that they've seen METs. Well, they didn't call it a MET, but they've had people come back and tell me, like, what is, we got the question, what is the resting oxygen consumption? So the resting oxygen consumption of a person will be 3.5 milliliters of oxygen per kilogram of body weight per minute. This is referred to as 1 MET equals 1 MET or metabolic equivalent equals, god dang it, got my E and my A backwards, 3.5 milliliters 2 per that's sort of the formula there. So now that's all well and good, but typically the most common method that we are going to use in order to measure someone's oxygen consumption is going to be your VO2 max. So the VO2 max VO2 max is going to be the volume of oxygen, the maximal amount of oxygen consumed. Okay, so your VO2 max is the most oxygen that you can consume, meaning that like if gas comes in, there's a lot of oxygen coming in, and there's very little CO2 coming out, then and you're still exhaling some of that oxygen, that means that you were not able to extract all of that oxygen. And by the way, like for the most part, you guys are all sitting down right now, like we're all in a resting position. Like we are exhaling a pretty good chunk of our oxygen. Like 30% of the air that you're bringing in isn't even getting used. A lot of it is being exhaled. You know, I'm bringing in oxygen. I used some of it, but I got rid of a good chunk of it. So, you know, if I start exercising like crazy, like let's say I start doing like jumping jacks and stuff, right? What that's going to do is that's going to, you know, start meaning that my muscles need more fuel. They're going to need more oxygen to do more work. So what they're going to do is they're going to consume more of those oxygen molecules, right? Like let's say oxygen came in and it went to my calves, and my calves were like, we're not doing anything right now. We don't need you, right? Well, then that oxygen is just going to keep traveling along its way, right? It's not going to really do anything. And maybe it'll work its way all the way back to the lungs, and then I exhale that molecule that I brought in. But if I start doing jumping jacks and I start using my calves a lot, what's going to happen is my calves are going to start needing to produce energy. So they're going to start consuming that oxygen in order to produce ATP. And the byproduct that's left over afterwards is going to be carbon dioxide. So that oxygen is going to get exchanged for carbon dioxide. Then it's going to travel back to my lungs, and I'm going to exhale the carbon dioxide. Okay. VO2 max is the amount of oxygen that you consume, right? It is generally considered the best form of like determining how cardiorespiratorily fit somebody is. Okay. Generally accepted as the best means for gauging cardiorespiratory fitness. Okay. So we have a lot of like, you know, tests for doing this. An actual VO2 max test, which we'll get into later on in our course, is going to involve wearing a mask that measures how many molecules of oxygen are going in versus how many molecules of oxygen are coming out. When that ratio is 1:1, you have hit your VO2 max, right? So if I brought in 10 units of oxygen and exhaled 3 units of oxygen, right? I didn't consume all of that oxygen, right? But if I brought in 10 units of oxygen and exhaled 10 units of oxygen, or 10 units of CO2, which means that I got rid of no oxygen, well, then now we know that I've hit my VO2 max. So if I were to do that test while also wearing a heart rate monitor, I know what I need to get my heart rate to in order to hit my VO2 max, in order for me to know how hard to work during my workouts, right? So when we say you want to work at 60% of your VO2, you know that that heart rate for you is whatever number you determine through your VO2 test. So it's a really cool test. We will get more into that in the next half of class when we get into our actual assessments. Now, we do know that dysfunctional breathing is obviously a big part of why we are doing these assessments, right? We do want to make sure that our client has proper posture in order to properly be able to bring in oxygen molecules. So if there's dysfunction there, that's going to lead to the inability of your body to produce energy effectively or efficiently. And so generally, alterations in breathing patterns are a very important part of our class. Alterations in, actually we'll say dysfunctional breathing. dysfunctional breathing patterns. Okay. Alterations right? So alterations in breathing patterns are going to lead to inefficiencies in our breathing patterns or in our energy production, right? If we can't bring in as much oxygen as we're supposed to, that is going to lead to dysfunction, right? It can lead to dizziness, shortness of breath, and then obviously just getting tired during your workout. You won't be able to like, the burn will be too much for you to be able to keep going. So one of the reasons we brought up shallow breathing patterns earlier is because shallow breathing patterns tend to rely on secondary respiratory muscles, right? Shallow breathing patterns tend to rely on secondary respiratory muscles. And what that leads to is this often leads to upper chest breathing in which the sternocleidomastoid, levator scapulae, scalenes, and upper trapezius muscles become overactive, right? This alters posture and can lead to things like biomechanic dysfunction, lightheadedness, and headaches. So that one's fine. That one's fine. Whoop. Armin, you're joining us in the morning. Welcome, welcome. So we do know that alterations like shallow breathing patterns, right? It leads to that elevated shoulder and forward head posture. That's going to keep you from raising your arms. It's going to keep you from being able to move, the way that we're designed. That's going to put more stress on, certain parts of the spine. When you start rounding like this, oftentimes your body has to counterbalance by either leaning back like this or maybe creating an anterior pelvic tilt like that, right? All of those things can affect your breathing patterns. And that is why we ask that question on the medical history questionnaire. Does your job require you a lot of stress? So in summary, your respiratory system is going to gather oxygen from the environment. As your cells use that oxygen, they're going to produce carbon dioxide as a byproduct, which will then be transported to the heart and lungs to be released through exhalation. We need to be able to transport that oxygen, and that's why we have our cardiovascular system, which is going to be made up of blood and blood vessels, and our heart, which is actually pumping everything. Obviously, if there's dysfunction in either of these systems, it's going to lead to overall dysfunction in the entire human movement system. All right, do you guys have any questions for today? Comments, concerns? That is about all I got for you. Thanks for putting up with all the drama this morning, guys. I don't know what that was all about. My theory, I've been thinking about this like in the back of my head this entire lecture. Do you remember how I was mentioning this? There's something weird about this like setup here. It's been like this since we started, but I don't know if it's because like I'm talking really loud and then it's bouncing off my computer and hitting me in the ear, but my ears have been plugged up every day. Like whenever I'm teaching, my ears are plugged up like every single day. They are always like whenever I'm lecturing, and I'm wondering if like my whole body just got finally just super nauseous because of that. Like I think I might have gotten seasick.
I know this is like really holistic-ish, but have you ever used the ear candles?
No, I haven't. No.
They work really good.
Yeah,
like,
I don't even use Q-tips. I don't like shoving stuff in my ears.
It like moves the smoke through your, and then when you pull the candle out, you see all the wax,
wax.
like build up in there. I mean, it's on you. But for me, they work. I use them on my kids, so it's
Yeah.
very holistic. Like but they work.
It's gooey.
So.
That's all right. All right, so let's go ahead and end the recording. We'll see y'all tomorrow.